So yeah, hey everyone, this is my project DSim, or how to accurately estimate the energy consumption of a system through simulation when a physical prototype is unavailable. In systems research, we regularly build systems that advance the state of the art, often making use of custom hardware accelerators to offload parts of the computation to. During this process, we are faced with many system as well as component level design choices. Some of those we can immediately dismiss by experience, while others need to be evaluated in order to determine the best one. So what does best one mean in this case? Usually the goal is to improve some end-to-end metrics for the workload that we have in mind. And generally these can be divided into two categories. First, there's performance, so for example the request throughput or latency for our workload. And then second, there's energy, so for example the energy consumption per request. And energy use is an important consideration since it directly influences the operational costs of our system design. Since we established that these end-to-end metrics are essential, let's talk about how can we actually measure them. And here it's important to differentiate between two options for implementing the hardware accelerator. When the system is designed to use an FPGA for this implementation, the evaluation is straightforward. We can just develop a physical system prototype and directly measure that as usual. However, if the system is meant to use an ASIC, it's really not that simple. The chip has to be manufactured first, which incurs huge costs and long fabrication times. So this option is out of reach for most systems research. Again, FPGAs can serve as an emulation since they offer the same functionality as an ASIC. However, FPGAs have very different performance and energy characteristics, so using them for emulation will result in an incomplete and inaccurate picture during evaluation. So this means we are facing the following challenge. How can we evaluate systems with custom hardware when physical prototypes are unobtainable? So let's now focus purely on measuring the end-to-end energy consumption of our system design. Here, we can make two important observations. First, energy use is spread across all of the components in our system. And second, energy consumption is generally made up of a static and dynamic part. And the dynamic consumption increases when transistors switch more frequently, and as a consequence, this now means that the dynamic consumption depends heavily on the concrete workload that we are running. And this is even further complicated by a commonly used hardware mechanism called clock gating, which inhibits the clock driving certain unused parts of the accelerator to save energy. So all of this really highlights that we need information about our workload to be able to accurately determine energy consumption. How do we get that? We can simulate our hardware and the workload before manufacturing it. And for this, I'm making use of prior work, namely Simprix, which enables us to take a physical system like the one that you see on the left here and translate it into a virtual test bed by replacing the individual components with existing simulators. And the key motivation for doing so is that this now allows us to run the full hard and software stack from the physical system, meaning we execute the actual workload with unmodified applications and operating system. And the virtual testbed is therefore able to capture complex interactions between components. So with Simprix, we can already measure the end-to-end performance. However, I haven't talked about energy consumption so far. So instead, here's my approach for measuring that, or rather estimating the end-to-end energy consumption with DSim. As already discussed, first I use Simprix to simulate the workload applications. And then during simulation, I collect the necessary workload metrics for accurate dynamic energy estimation. And speaking of that, with DSim, I make use of the fact that there is already existing work for estimating the energy consumption of the individual components in our system. And applying these existing energy models, I get separate numbers per component. And in the end, I can just simply sum this up into one full system estimate. So let's have a closer look at evaluating this simple system made up of a CPU with a hardware accelerator attached over PCI Express. The CPU is simulated by the architectural simulator Gem 5, and it runs the OS, libraries, and the workload application. The hardware accelerator, on the other side, is simulated by a cycle-accurate RTL simulator. And Here I'm using the example of a JPEG decoder, but you can of course simulate anything for which you have the RTL code for. And then there's the PCIe connection connecting your two, and this one is taken care of by Simbrix. So how does DSim now estimate the energy consumption in the system? Well, Gem 5 already comes with an online energy model, meaning energy is computed directly during the simulation. And this energy model uses the simulated CPU's execution statistics like the current processor frequency, the number of instructions executed, and cache misses, which are continuously collected over small time spans. In comparison to that, the accelerator is estimated offline. So here I configure Verilator to trace the circuit signals. And after the simulation completes, this gives me a trace file which I feed into the energy estimation tool from a hardware toolchain. And in fact, all of the major toolchains already come with energy estimation and accept some form of circuit signal information to provide you with more accurate results. So now that we discussed the approach, I wanted to validate whether it actually works. And for this, I used an SOC FPGA board to physically prototype the system shown on the previous slide. And the SOC contains a CPU on which I run the operating system as well as the application for the workload. So during this experiment, I measured the energy consumption of purely the FPGA to obtain the ground truth, and I then compare this with a simple workload agnostic estimation using Vivado as well as what I get from DSim. And here I'd like to stress that even though I can, of course, simply measure the physical system here, ultimately DSim targets systems where you don't have that. Okay, so here's the ground truth that I measured in the physical system. And next we compare it to the simple workload estimation from Vivado, and as you can see, this is far off. And now with DSim, we actually use the exact same estimation tool in Vivado, but the only difference is that we are now introducing the accurate workload information, and with that we get an estimation that is pretty close to the physical system. Next, I ran a different workload where the JPEG decoder is completely idle, which is why I'm reporting power consumption here. And as we can see, the simple estimation is still off, and again, DSim gets much closer, in fact, only slightly overestimating the ground truth. So these previous results that we looked at, these results look really promising. However, there's a lot of stuff that I still want to look into. First of all, I'd like to do further validation, especially for the CPU energy model, which we haven't looked at so far. Second, the longer-term goal is to enable full network system estimation, and this mainly means incorporating additional energy models, for example, for SmartNICs or for programmable network switches. And third, and this is actually a short-term goal, is to improve the scalability and accuracy of DSim by sampling the workload information. So what do I mean by that? So currently, for estimating the accelerator, I'm recording this complete circuit signal trace for the whole workload. And I left out a tiny but important detail earlier, which is that the hardware energy estimation tools actually work with statistical data in the form of signal activities, which I need to compute from this trace. And the way I'm currently doing this is I'm doing it over the full time span of the workload, which basically means I'm averaging from beginning to end. And this has two key problems. The first one being scalability. So collecting a circuit signal trace over this whole time span means a lot of data. And for the JPEG decoder, for decoding a single image, this resulted in, so I was simulating 250 milliseconds and got a 13 gigabyte trace file for that. And second, this has huge implications for accuracy. For the validation that we saw earlier, this works since the workload is pretty constant. However, generally the activity of signals on hardware accelerators can significantly change over time due to our workload. So here's my proposal, which is to instead sample the workload characteristics uniformly across components and compute the statistical metrics over small windows. And this also gives the user more control to directly trade off scalability and accuracy. Okay, so to sum up, DSim enables systems researchers to evaluate the full picture of a system, concretely the end-to-end energy, and combined with Simbrix also performance when the physical prototype is unavailable. And as a final remark, I'm going to open source the project shortly. So Do you have any questions?
Questions?
Yeah, hi, Tils Maika from TU Dresden. Very interesting work. I have actually a question. Being someone myself who is working with energy, one important part that you usually have if you look at energy is if you have components, they consume some energy and you have still some huge static parts in your system. Do you have any idea how to integrate it in your simulation, or is it already integrated in there? I wasn't sure from your presentation.
Okay, so the static parts, if we're talking purely about the hardware accelerator, the static part is also estimated by the, I used the example of Vivado, but essentially for every toolchain it would spit out independently the static power consumption and the dynamic power consumption, and then for the other stuff you need to take care of that in your model. So for example, the way the Gem 5 approaches this is it looks at the temperature and the frequency, that's what I mentioned earlier, of your chip, and using that to determine the static energy consumption.
Mm-hmm. And there are also other parts in your system that are depending on the utilization of your system, for example, like fans or your power supply unit that depends on the voltage and stuff like that. Is this somehow integrated, or?
How you can integrate it is, since I'm taking this modular approach where I just sum up individual estimates, the thing about the static part of the power consumption is it's static throughout your workload. So it's essentially just adding a constant on top of that. So here what you could do for your fan, just measure the power or the energy consumption of that and just add it on top. And that's how you get the whole system.
Okay, thank you.
We'll take one quick question.
Hi, Alexander Krause, TU Dresden. Given the FPGA synthesis is kind of a more or less randomized process where you are relying on a seed, did you evaluate how much randomness your FPGA image has in terms of energy consumption?
Oh, that's actually really interesting. I didn't know about this so far. No, I did not evaluate this, but thank you for the idea. I'll definitely do that.
Thanks.
Okay, let's thank the speaker.